So in today's video, we're going to be discussing chapter 5.5, which looks at complex eigenvalues and complex eigenvectors. So far, when we've looked at eigenvalues and eigenvectors, we have taken a matrix A that has real entries, so that they're all real numbers. We normally deal with whole numbers. And we find its eigenvectors and eigenvalues. And so far, we've only looked at the possibilities where an A has a real eigenvalue and a real eigenvector. However, sometimes when you solve that characteristic equation, you can find that a real matrix A can actually have complex eigenvalues, and hence it can have complex eigenvectors. So we're going to look at that case today, and we're going to look at geometrically what that would mean. So if I had a matrix A and I multiplied it by some vector x, what does that look like if the matrix A actually has complex eigenvalues and eigenvectors? So as I said, so far we've just looked at a matrix A that, when we've looked at its characteristic equation, it has degree n, but that degree n polynomial has split into linear factors. Okay, so it's got linear factors, which means that we have these n eigenvalues, not necessarily distinct, but they've all been real. The problem is sometimes that characteristic polynomial that we find when we solve the determinant of a minus lambda I is equal to 0, we solve this, we get a degree n polynomial in terms of lambda. Okay. Now, so far, it's split into linear factors, and then we can find the n eigenvalues that may not be distinct. But sometimes you can find that it won't split into all linear factors. Sometimes you can find that you could get a factor in this polynomial such as lambda squared plus 4. That could be a factor of the polynomial. Now that does not factor into two separate linear factors. So if you got something like this, because it doesn't factor any further, we've got to find the roots of that polynomial. Okay? So you could end up with some characteristic polynomial, let's say for a 3 by 3, where you could have something that would look like this. Okay? Now we know that lambda equals 3 would be an eigenvalue, but the question is, what would the eigenvalues of this look like? Well, again, if we set that factor equal to 0 and we solve, what you actually find is that lambda is equal to plus or minus 2i. So we have complex eigenvalues, and as we'll see, they always come in pairs. So you will always have a complex eigenvalue, and its complex conjugate will also be an eigenvalue of that matrix, as we'll see here. Complex eigenvalues come up a lot in real life cases. They come up a lot when you look at vibrations and rotations in dynamical systems. So they are actually really useful to know, and you may come across them more in differential equations or in some of your physics classes later on. So they are a really useful thing to know and to learn about. So as always, the fundamentals of complex eigenvalues and complex eigenvectors, the actual theory behind it and how we solve for them, is exactly the same as we would do if we had real eigenvectors and eigenvalues. So we're going to go through an example and try to solve one of these characteristic equations where we actually end up having complex eigenvalues and then finding its associated basis for the eigenspace. Okay, so we're going to do that, and then we're going to talk about geometrically what this would look like. So the example that I want to go through, and we'll be coming back to this example later on, so make sure you have this one written down. We want to find the eigenvalues and a basis for each eigenspace for this matrix. So we're finding the eigenvectors and eigenvalues exactly as we would like you did in your test. Okay? So we solve our characteristic equation. And in this case, you should get a degree 2 polynomial. So we want the determinant. I'll put this in straight lines to show the determinant. A minus lambda I would be 5 minus lambda 1, negative 2, 3 minus lambda. And we want that determinant to equal 0. So with the determinant of a 2 by 2, we would get that. And then if we multiply that out, we're going to get lambda squared minus 8 lambda, then plus 17 will equal 0. Now, you can't split this into linear factors. You can try if you want to, but it doesn't actually work. I'm actually going to use the quadratic formula to solve for this. So I've got lambda is equal to 8 plus or minus the square root of 64 minus 4 times a times c is going to be minus 68, all divided by 2, which is going to give me, when you do that, you're going to get 4 plus or minus I, because 64 minus 68 is negative 4, okay? Square root the 4, you're going to get 2, so that's going to be 2 multiplied by the square root of negative 1, which is I, and then if you've got 2 times I divided by 2, you're just going to get I, okay? So that means that we have 2 different eigenvalues, okay? We're going to get 4 plus I and 4 minus I. So you can see that they occur in a complex conjugate pair, okay? So complex eigenvalues always occur with their complex conjugate. For those of you that haven't maybe done complex numbers in a while, or if you haven't seen them before, a complex conjugate is just where the imaginary part of the number is the opposite sign of its complex conjugate. So if you've got 4 plus I, its complex conjugate is 4 minus I. Okay, so you always take the negative of the imaginary term. Okay, so we've got our 2 eigenvalues. The next question is, what are the bases for the associated eigenspaces for each one of these eigenvalues? So if lambda is equal to 4 plus I. Now we're going to solve for the basis of the eigenspace, find those eigenvectors in exactly the same way as we would if we were dealing with real numbers. So you're going to solve for a minus lambda I multiplied by x is equal to 0. So that's going to give you a minus 4 plus I times the identity times x is equal to 0. So what that means is a minus lambda I is going to be this thing here, but I'm going to plug in lambda is equal to 4 plus I. So that's going to make a minus 4 plus I times the identity. That's going to become 1 minus I, negative 2, 1, negative 1 minus I. X, it's got to be 2-dimensional vector. And 0, 0. Okay, so just as a heads up where I got this from, so I do a minus 4 plus I times the identity. So that just means I plug in lambda is equal to 4 plus I into both of these, and I should get this matrix. Okay. Now, normally when we get to this point, this is the one part of it that's very slightly different to how we solved before. Normally when you got to this point, you would row reduce, and then you could solve for x1 and x2. But you always know that if lambda is an eigenvalue, then this equation here is going to have a free variable, okay? Which means that this row here, multiplied by this, is going to be a multiple in the end of this row with the dot product of this, okay? So whichever row I choose to use, at the end of the day, I should be able to make them equal the same thing. So whether I do 1 minus I, this is actually the row I'm going to use, multiplied by x1 minus 2x2 is equal to 0. I could use that line, or I could use x1 plus negative 1 minus I x2 is equal to 0. Okay, I could use either one of these and I should end up with the same relationship between x1 and x2, because I know that 4 plus I is an eigenvalue. So I know it's going to have an associated eigenvector, which means that this thing must have a non-trivial solution. So you should get that same relationship between x1 and x2. It may require some simplifying, which it does in this case, but you should get that same relationship no matter which one of these equations you use. Okay, you actually get from this equation to this equation just by multiplying through by 1 minus I. Okay, so if you multiply this by 1 minus I, you get this, and if you multiply through this thing by 1 minus I, you're going to get this. Okay, so if you want to try it out, you can. Just remember that I times I is -1. So you can use either line here. Okay, I'm going to use the top line, which is going to give me 1 minus I times x1 is equal to 2x2. Okay, I tend to go for the simplest thing possible for x1 and x2 that does not involve fractions. It just makes it so much easier. Okay, but you can do whatever you want as long as it is in keeping with this relationship between x1 and x2. You could choose whatever basis you like, okay? But again, I choose the simplest thing possible. So I can see from this equation, if I set x1 equal to 2 and x2 equal to 1 minus I, I'm going to get the same thing on both sides. So in this case, my basis for the eigenspace associated with 4 plus I, so the basis for the eigenspace associated with lambda is equal to 4 plus I, is going to be 2, 1 minus I. Okay? So I've got my basis for that eigenspace. You can do the exact same thing for the basis of the eigenspace that is associated with lambda is equal to 4 minus I. So for lambda is equal to 4 minus I, you're going to go through the exact same thing again, okay? So for lambda is equal to 4 minus I, you would have 4 minus I in here instead. So that's going to make this thing 1 plus I, and this thing -1 plus I, okay? So you're going to go through the same thing again. And what you should find, you can go through it yourself, but what you should find is that the basis of the eigenspace associated with this eigenvalue is just this, okay? So you can also see that the basis of the eigenspaces are actually complex conjugates of one another as well, okay? So keep that in mind when you do this, because you should see this come up time and time again whenever you deal with eigenvectors and eigenvalues. Okay, I want to go through something very quickly algebraically before we move on to like more of an application of this. What you can see, and we'll use this as an example here, take the vector 2, 1 plus I. Okay, so take that vector. You can split any vector into its real and imaginary part. Okay, so let's say we had x is equal to 2, 1 plus I. Okay, you can split that vector into its real and imaginary part. So you can split it into 2, 1 plus I, 0, 1. Okay, those two things are equal. Your top line would be 2 plus 0, which is just 2. Your bottom line would be 1 plus 1 times I, which is just 1 plus I, which we have, okay? So you can always split one vector that's a complex vector into its real and imaginary part. This vector here we call real x, and this vector here we call imaginary x. So the vector that you're going to multiply by I is the imaginary part of x, and the vector that just contains the real part that's never multiplied by I, that's the real part of x. Okay. Another piece of notation for you, if you take the complex conjugate of a vector, you take the vector and then you draw a line above it. So in this case, the complex conjugate of x would be 2, 1 minus I, okay, which was actually the basis of the eigenspace for the other eigenvalue. So keep that in mind, but that's just a notation for you. So if we let R be a complex number, so R is in the complex numbers, then we're going to let X be a vector that's in Cn. So it's very much like Rn, okay? This is going to be a vector with n entries, but some of them may be complex, some of them may be real, okay? So X is going to be in the complex n space. And then we're going to let B be an n by n matrix or an m by n matrix. It doesn't necessarily have to be square. It can be an m by n matrix. So we're going to say that it's m by n, okay? And some of its entries may be complex, okay? And what you can actually see is that if I take r multiplied by x and take its conjugate, that will actually equal the conjugate of r multiplied by the conjugate of x, okay? The same goes for if you actually multiply a matrix times a vector and take its conjugate. You can just multiply the conjugate of each one. Same goes with a matrix. So if I did RB and take its conjugate, that's the conjugate of R times the conjugate of B. And it actually works with two matrices. So if I take two matrices, as long as they multiply together dimension-wise, so you'd have to have like an m by n and an n by p or something, okay? If I take B times C and take its conjugate, it's just the conjugate of B times the conjugate of C, okay? We're not going to go into the details of this. I think some of this is in the homework in 5.5, but some of this is kind of complex to prove. But just be aware that that is the case when you multiply a matrix times a vector, or a complex number times a vector, or a complex number times a matrix. Okay, we're going to use that now. So if we say that A is a real n by n matrix. So we're now dealing with square matrices. So A is a real n by n matrix. If I decide to do A times X, okay, now X could be complex, okay, X is still in Cn, okay. If I take its conjugate, okay, I know from above that that is equal to the conjugate of A times the conjugate of X. So what I am doing here is I'm taking the complex conjugate of every single entry in X. Okay, so if I had like a 1 minus I entry in X, I'm making that 1 plus I. Okay, so I'm taking the conjugate of every entry in X. And what this also says is that I'm taking the complex conjugate of every entry in A. Problem is, A is real, okay? It doesn't have any complex entries. So by taking the complex conjugate of A, I'm not actually changing the matrix. So that's just going to be A times the complex conjugate of X, okay? So what that tells me is if I want to do A multiplied by some complex X, okay, that's going to be A times X and take its conjugate. Now, if X is an eigenvector, okay, it's going to have associated eigenvalue lambda, okay? And that, as we've seen above, is equal to that. So what that tells me, okay, we start out with A times X is equal to lambda X, okay? X may be complex, and so can lambda. Okay, so if X is complex and lambda is complex, okay, but A is real. So we're dealing with a real matrix that has complex eigenvalues and eigenvectors. What I have shown here is exactly what that previous example showed us. If lambda is a complex eigenvalue with complex eigenvector X that's associated with it, I also know that the complex conjugate of lambda is also an eigenvalue of A, and the complex conjugate of X is its associated eigenvector, okay? So it's also the basis of the associated eigenspace. So let's come back here and you can see this, okay? What we showed the first time was that lambda is equal to 4 plus I was an eigenvalue, and its associated eigenvector was this. But I also know that the complex conjugate of this lambda is also an eigenvalue. 4 minus I is also an eigenvalue. And the complex conjugate of this eigenvector is also an eigenvector. So I know, this proves this algebraically, that if lambda is a complex eigenvalue with complex eigenvector x, then the complex conjugate of lambda is also an eigenvalue of A, with the complex conjugate of x being its associated eigenvector and the associated basis for the eigenspace. Okay, so we'll write that down quickly. So if lambda is an eigenvalue of A with eigenvector x, then the complex conjugate of lambda is also an eigenvalue with eigenvector complex conjugate of x. Okay, that means that if you have one complex eigenvalue, you must have its complex conjugate as another eigenvalue, which means that these come in pairs. You are never going to have an odd number of complex eigenvalues. Okay, they are always going to come in pairs. They are always going to come in pairs as conjugates. So keep that in mind. If you ever end up with an odd number of eigenvalues that are complex, you know you've gone wrong somewhere. You should always have an even number of complex numbers as eigenvalues because they come in pairs of complex conjugates. Okay. Next, I want to look at what this does geometrically. So okay. This actually has some more geometric theory behind it. It's not the easiest thing to follow, so if you do need to watch this again, feel free. It is also in the textbook if you need a second resource. Okay. I'm going to use the same notation as the textbook uses just so that you can see what I'm doing if you do need to look at the textbook. I also have this in my notes where I've reworded it slightly different to what the textbook has. So hopefully between the three different resources, this video, my notes and the textbook, you can hopefully piece the pieces together. But please feel free to ask me questions about this because it is not the easiest thing. Okay, so first I'm kind of going to work backwards and then work forwards, okay, just so you can kind of see what happens. I'm going to do all of this in 2 by 2, by the way. It does extend to higher dimensions. We don't look at that right now. We're just going to stick to 2 by 2. Okay, I'm going to take a matrix C, okay, and I'm going to say that C has this form. Okay, A and B are real. So A and B exist in the real numbers, okay, and C is of this form. What you can see if you go ahead and do this, if you figure out the eigenvalues of this matrix, okay, so you'd be solving the determinant of C minus lambda I is equal to 0. If you solve that for lambda, what you actually find is that the eigenvalues of this matrix are A plus or minus BI. Okay, so I know that I've got lambda is equal to A plus BI as one eigenvalue and A minus BI as another eigenvalue. Okay, just because I want to kind of work with this matrix slightly differently, I'm going to say that R, okay, is going to be the magnitude of lambda, which is going to be the square root of A squared plus B squared. Okay. What I'm going to do, using that value R, okay, I'm going to say C is equal to R times this matrix. So what I'm actually going to do is divide by lambda on every entry in that matrix, but then multiply by lambda out the front. So all of those R's would actually cancel out. Okay, and R again is just the square root of A squared plus B squared, where A plus or minus BI is the associated eigenvalues, okay, for this matrix. What you can do with this matrix here, okay, remember, if you multiply by the identity, you don't change the matrix in any way. So if I multiply this thing through by the identity, I am not changing the structure in any way, okay? It's still going to be the exact same matrix. So what I'm actually going to do is say, okay, this thing is equal to R multiplied by the 2 by 2 identity multiplied by this matrix again. Okay. Now I've got R multiplied by an identity. I'm scaling the identity here by the factor of R. So multiplying through I'm going to end up with this. Okay. You'll see where this is going in a minute. So let's draw a quick diagram for this. So if this is our real axis and this is the imaginary axis, okay, remember A was the real part of the complex number and B was the imaginary part. So I'm going to say that A is here, B is up here, and this being the square root of A squared plus B squared is there. So this is R, B, and A, okay? And then I'm going to take the angle here between A and R. I'm going to take that to be the angle phi, okay? So what you can actually see here by SOHCAHTOA is that A over R is going to be cosine of phi. B over R is going to be sine of phi. So A over R is equal to cosine of phi, and B over R is equal to sine of phi. Okay? And then what we can say is this here will equal R, 0, 0, R, and then cosine phi negative sine phi, sine phi, and cosine phi. Okay. Phi is known as the argument of the complex number. So in this case, phi is the argument of our eigenvalue. But for those of you that have done some matrix theory before, you'll recognize this matrix to actually be the rotation matrix by phi. Okay. So what this matrix actually does is when you multiply it by a vector, it rotates that vector by phi. Okay, so in this case, we're dealing with a 2 by 2. So it's going to rotate in the R, well, in this case, in the C square plane, it's going to rotate it by phi. Okay, so from here, what you can see is that C is made up of something that's going to scale a vector and something that is going to rotate a vector. So if we take t of x to be c multiplied by x, t, the mapping, is just a composition of a rotation through the angle phi followed by a scaling of the factor r. So what it's going to do is it's going to rotate that vector x by phi, and then it's going to scale it by a factor of r. If you would like to see a picture of this, just to kind of visualize it a bit more, right at the top of page 301, there is figure 3 that shows this, and it actually shows the rotation of that vector and then scaling it just so that you can see it as a picture. I'm going to relate all of this back to an example that we just did, okay, to show you what this matrix C actually does, what it means for us, okay, and the fact that it's composed of this rotation matrix and this scaling matrix. What has that got to do with our matrix A that had A plus bi as an eigenvalue? Okay, what has all of that got to do with a matrix A? Okay, because what we've done here is we've been decomposing this matrix C. Okay, but what has that got to do with a random matrix A? Okay, that's what we want to look at. So let's go back to our original example. Okay. And that had, I'll just write down one of the eigenvalues for now. And then V is equal to 2, 1 minus I. Okay. So I've got one of the eigenvalues and the associated eigenvector, and we already know that the complex conjugates of these are also an eigenvalue and an eigenvector. I'm going to take a matrix P, okay? And the matrix P is going to have 2 columns. I'm going to take the first column of P to be that real vector part of V, okay? And the second column is going to be the vector that deals with the imaginary part. So for V that we have here, okay, the real part would be 2, 1. The imaginary part would be 0, -1. So I can split V up to be 2, 1 plus I times 0, -1. Okay, so I've got the real and the imaginary part put into a matrix. Then what I'm going to do is I'm going to take a matrix C that is similar to the matrix A. So C, I'm going to take at the moment to be P inverse AP. Okay, so C is going to be similar to A. So P inverse AP, if you want to go ahead and work this out, you should get -1/2. Hopefully I can get all of this in one line. I might actually go onto a second line just to make sure that I've got enough space here. This is going to equal -1/2, -1, 0, -1, 2, multiplied by 5, -2, 1, 3, times 2, 0, 1, -1. Okay, so I've taken P inverse is this -1/2 times -1, 0, -1, 2. This is the matrix A that we started with, and this is P that we created up here. If you multiply all of that together, what you end up with is 4, 1, -1, 4. Okay, so this relates back to what we were just doing. Okay, this matrix is of this form. So what I can see here is if I take my eigenvalue to be of this form, it's actually got a negative in it right now. If I take lambda to equal A minus BI, I know A plus BI is another eigenvalue, okay? But if I take this to be my eigenvalue, which we know at the moment is 4 plus I, that would mean A is equal to 4 and B is equal to -1. Going back to what we have here, if I plug in A is 4 and B is -1, I get this matrix C. Okay, so we know that C that is of this form is similar to the matrix A that we started with, where A had the eigenvalues A plus and minus BI. So we know that A is similar to a matrix of this form. And the way that we constructed P was out of the basis of the eigenspace that went with that eigenvalue. Okay, so we split P into the real and imaginary vector as its columns, and then the similar matrix to A was constructed out of the entries from the eigenvalues. Okay, now we know a lot about this matrix C. We've just talked about this matrix C. Okay, we know that C is formed of a scaling factor, R, which is the square root of A squared plus B squared, and this rotation matrix. Okay, so what C represents is a scaling and a rotation. So what we have here, C is equal to P inverse AP. I'm going to rewrite that as A is equal to PC P inverse. You can get that literally by multiplying both sides through by P at the front, multiplying both sides through by P inverse at the back. Okay, if you do that, you're going to get this. And what you can see here is I have a matrix P, which we'll talk about in a minute. Then I've got a matrix C that is comprised of this scaling and this rotation. And then I am undoing what I did at the start. So this is what this matrix A that is comprised of these complex eigenvalues and eigenvectors that it has, okay? When a matrix A has those complex eigenvalues and eigenvectors, it can be split up in this way, where P and C are formed using the eigenvalues and eigenvectors of A. And what we can show by doing that is how this matrix A acts as a linear transformation on a vector. So if you had T of X was equal to A multiplied by X, we're going to look at what that actually does. And there's a really good diagram. It's figure 4 on page 301. So it's literally just underneath the other one that I was talking about a second ago. That diagram is going to show you exactly what this does. And it's really good to kind of see it visually again. So what do we know so far? Well, we know that A is similar to this matrix C, where C represents a combination of scaling by a factor and a rotation. And that scaling and that rotation depend on what the eigenvalues of A were. And the way that we get this similarity is using this invertible matrix P, and P is determined by the eigenvector that is associated by the eigenvalue lambda of A. Okay. So let's see what happens when I do A multiplied by a vector X. Okay. First thing I'm going to do is actually do a change of variable. Okay. I'm going to let X equal P times U. Okay. All this is going to do is it's going to change a variable. And then because we've got a P inverse in there, it's actually going to change it back at the end. So it doesn't matter that we're doing a change of variable here. Okay, it's just like doing a substitution and then undoing it again at the end. Okay, so it's not going to affect anything. We're just doing like a substitution type thing here. Okay, if X is equal to P times U, I can rearrange that to say that U is equal to P inverse X. Okay, so when I do A times X, I'm doing PC P inverse X. Okay. Now, P inverse X is U. Okay. Now, what I've done here is I'm doing C times U. Okay. If I do C times U, that's the same thing. If you come back up here, I could have A times P is equal to P times C. So PCU is equal to APU. And I know that P times U is equal to X. So I end up back where I started. Okay. So what does this all mean? By doing P inverse X, what I am doing is changing X into this variable U. Okay, so all P inverse does is give me a change of variable. Okay, it's giving me a substitution. What C is then doing is it's then scaling and rotating that change of variable that I have. So I'm going from X to this change of variable. I'm then scaling it and rotating it. And then what P is doing is it's going to take it back to my initial variable, X. Okay. So what I'm doing is I'm starting at X. I'm doing a change of variable to U. I'm going to scale and rotate U and then transform that vector back to X. Okay. So all I'm doing is doing that scaling and rotation in terms of a different variable and then bringing it back to where I started. That's all you do. As I said, there is a really good diagram. It's figure 4 on page 301 that shows this. But that is all these matrices do, okay, is that they're going to be scaling and rotating that vector that you start with. Okay. So let's put all of this into a theorem. Okay. So again, we're only doing 2 by 2 theory here. So let A be a 2 by 2 matrix. With real entries. Okay, so you start out with a real 2 by 2 matrix. But that real 2 by 2 matrix is going to have complex eigenvalues. Okay, and for the sake of the signs that we use, just so that we can make the matrix look like we want it to look, I'm going to say that it has eigenvalue A minus BI. It also has the eigenvalue A plus BI. We know that it's got the complex conjugate eigenvalue. But right now, just to make those matrices look how I want them to look, I'm just going to be dealing with this eigenvalue. Okay? And it's got a complex eigenvector that's associated with that eigenvalue. I'm going to call it V. And that is also going to be complex. Okay, if you've got the complex eigenvalue, it's going to have a complex eigenvector. Then A can be written as PCP inverse, where P is just a matrix with 2 columns. One of those columns is the real part of that eigenvector, and the other column is the imaginary part of that eigenvector. Okay, P is going to be a real matrix. Okay, P's got all real values in it. This is just the vector that deals with the real part. This is the vector that you multiply by I to get the imaginary part. And then C, okay, this is why we wrote lambda in this way. It's going to be written as A minus B, B, A. And the reason that we want it in that form is because then when we do R multiplied by this matrix divided by R, okay, just when you try and rewrite this matrix to look how we want it to look, we then get that matrix where we know it's a rotation matrix. So that's why we write it in that form. Okay, so C represents a rotation and a scaling okay. So we know that we can always let A be similar to this matrix C, okay? And it's going to be similar using this invertible matrix P that is made up of the associated eigenvector for that eigenvalue lambda, okay? And then we know that what multiplying by this matrix A does is it's going to change the variable at the start. It's then going to scale it and rotate that vector, and then we're going to bring it back down to the vectors that we started with, bring it back down into that same X set of vectors, okay? So you take it from x, you do a substitution in terms of u, you're then going to scale and reflect u and then bring it back down to x. Okay. So this is kind of the start of all the eigenvalue, eigenvector stuff in terms of the complex space. It's not the easiest thing to see. Hopefully with this explanation, with my notes and with the textbook, you can get a hang of it. I will give you some homework problems that you can try out to find the eigenvalues and eigenvectors if they are complex, just so you can kind of get a hang of this and you can see those matrices that are similar. If you do have any questions, please feel free to ask me. And I will see you in the next video.